Okay, so let's finish up this first topic here. So we left off with the final part of this was just to teach you a bunch of cool little mechanisms that could be useful in your life as you go out into the world. To be aware of some classic examples here. It's good to know about it so you have more arrows in your quiver to use if you ever need to design some of these. So I'll talk about some classic mechanisms just briefly. This will be a short video. Okay, so there are snap action or bistable mechanisms, or actually multi-stable mechanisms out there. And they usually always have a spring or some kind of compliance in it. I'll be covering this in my YouTube channel and compliant mechanisms. But you can see on the top left, there's a bar there. There's a pin joint up at the top, and there's a spring in between another bar with a pin. And on the right side, if you bend that up, it'll kind of compress that spring and until it gets over to another stable state, and it'll snap up and hit on the top left there. And so you can see it's kind of, there's two, if you plot the energy in the system, it kind of looks something like this if it's a bistable mechanism, where, you can think of it, you put a ball on top of this hill, it's not very happy, it's not stable. It'll either roll down on this side or roll down on that side where it's much lower energy well and is stable. And so you can kind of see it's stable when this switch is either up or stable when the switch is down. And this is another way to view a rigid mechanism switch with a spring in it. The spring would compress and then kind of snap back when that snaps to the other side. So you can do this, instead of having rigid mechanisms that are assembled with a spring in it, you can just make one big monolithic body as a compliant mechanism. You can imagine this would be like a gate that's it's open here, but then you push this down, it ticks there. And these have really satisfying ticking, snap action kind of sounds and stuff. But you can create switches where things are stable and that they stay in certain configurations, so you give them a certain amount of force and then they snap to the other one. Very useful mechanisms. Okay, this is a differential mechanism, a differential screw in particular. So you can see, so first of all, sometimes people want really small motions for large input motions like a transmission. So you could imagine if you want to you have a motor attached to like a lead screw, and you want the motor to rotate a lot of times but only have the lead screw advance a tiny amount, well, then you'd want a really small pitch. You'd want your threads to be really tight together so that for lots of rotation you get a small translation. But there's only so much you can fabricate small threads that are packed together that tight. So if you want to get even smaller output for a large input, one trick you can use is a differential screw, where you can see this screw here, even though it changes diameter, but it's all the same screw, so they're forced to all rotate the same amount. And this is the ground, and there's a slot cut in it, so that this body is not rigidly attached to the slot, but it's only allowed to slide in it. It can't rotate with the screw. So it slides inside this slot as these things rotate. And what can happen is you can get differential motion by tuning the pitch and the diameter and these things. As you rotate, you can cause this final block to move very, very small amounts or do what you want. So that's a concept of differential screw kind of mechanism. This is a ratchet mechanism. It's kind of like a turnstile. It's in locks, jacks, clockwork. They use these in clocks all the time. You can see some really cool, how clock work videos on YouTube, and you'll see ratchets in there. And basically, they're one-way mechanisms. They can only rotate one way, and if you try and rotate the other way, then they get jammed. And what you need is a spring having that mechanism hold it in there. And so it's just a one-way kind of turnstile thing. Ends up being very useful in mechanical design. A mechanism that freely rotates one way but can't rotate the other way. Okay. Indexing mechanisms. These are really useful, neat mechanisms where, sometimes, like I said, you want a motor, in the last video, you want a motor to keep continuously rotating without stopping. It just takes less energy. It's easier on the motor if you just plug it in, turn it on, and it just goes forever. But sometimes the output you don't want to continuously rotate. So if you imagine if I just continuously rotated this kind of gear, but notice there's no teeth on this side, but there's just teeth there. So the whole time this gear is rotating, this guy won't be moving until the teeth catch this sector, and then it'll rotate, and then it won't rotate. So as this continuously rotates with this clever design, you can cause the output gear to just rotate and then stop, and then rotate and stop, rotate and stop. So you can get variable output speeds and cause things to wait. This is a Geneva wheel that kind of does the same thing. You can see this one keeps continuously rotating, but every full rotation this just turns like a quarter. Okay, and here it's just dead stopped until it rotates. Okay, and you can play with this and do many more interesting things. Okay, so here it speeds and it waits a while, and then it does a double spin, and then so it does. There's some neat things you can do with this indexing mechanism, and you can invert the Geneva wheel to do something like this. This is another kind of indexing mechanism, also very useful to take continuous rotation and turn it into an output that is more stop and go. Okay, reciprocating mechanisms. So like I said, one of the best things a mechanism does is it takes a continuous motor and turns it into something that rocks back and forth, or preferably transforms a rotation from a rotary motor into just a linear motion that oscillates back and forth. That's essentially in your car. You're doing the opposite. You're taking an oscillating back and forth and turning it into continuous rotation of the the engine shaft and everything. So that's a very useful skill. So they're called reciprocating mechanisms, and you can see in this example, this wheel in the center is just continuously rotating, but it's transforming its motion into a back and forth translation. Here's another crazier way to do it. Probably not the greatest way to do it, but kind of looks cool. Here's another way. You can see the input motor is again the green wheel. It's just continuously rotating the same direction, but that brown piston is kind of pushed up and down by these clever gears. Okay, this is a very classic reciprocating mechanism. The motor would be attached to this arm, and it just continuously rotates and causes this piston to go back and forth like a cosine. In fact, you could calculate very easily if you know the length of this. Whatever the angle of that motor is, you do the length of that times cosine that angle, and that's the output. And you can see here's the displacement, and the velocity is, of course, the derivative of that. Okay. But sometimes you don't want a nice sinusoidal undulation output. Sometimes you want a continuous rotation input, but you want maybe a quick return kind of mechanism. So that's what this is. This is a quick return mechanism. So oftentimes, for one direction of the stroke, you want it to be slow as it's doing some useful work. It's like pushing something nice and slow. But then when it's done its work, you want it to get back to where it started as soon as possible, because that's like a waste of time to while it's resetting, and then you can get back to doing work. So oftentimes you want the pushing to be slow, and then you got to whip back quickly. So you don't want a nice sinusoidal undulation. Well, there's mechanisms that can do that. You can see top left, it's the velocities and displacements are offset there. Okay, sometimes you want it to reciprocate, oscillate back and forth, but different amplitudes. Like for the sewing, the needle in a sewing machine, the old school 1800 sewing machines would use a Wanzer needle bar mechanism, and you can see how that works here. It's kind of a very clever little mechanism that's designed so that some amplitudes are small and some are large, and the needle goes in and out of the clothing on this end here. So these are cool to take old school sewing machines apart. Okay, other mechanisms can turn a continuous rotation. So this blue arm back here would be attached to the motor, and it's just continuously rotating, but the rest of the mechanism draws a very interesting path. If you stuck like a pen in here, it would draw this nice path that doesn't look at all like a continuous rotation, and it would do it at different speeds. So you can do this part really slowly and then this part very quickly. And sometimes you go into museums and you see a continuous motor attached to a really complex mechanism, and someone's put a pen in and it's drawing really cool patterns. And so that's a curve generating mechanism. Okay, this is a pentagraph linkage. This was used way ages ago, before copy machines and stuff. If you were writing a letter, for instance, and you wanted to write 2 copies at the same time, well, you could use a pentagraph, slightly configured differently. In this case, if you were drawing, tracing this small one, this would magnify the exact same design. Or if you wanted to draw a smaller version, you could draw here, and it would make a smaller version. But you can configure this so they're the exact same size, and then you could write a letter, and this exact same letter would be written simultaneously. Of course, it's really annoying because you're sloshing around all that dynamics, but people, believe it or not, use this. But it's also kind of cool because you can take the coarse resolution of your hand and do very fine artwork that's really small. It de-amplifies everything you draw. So it can be used for copying, engraving, sculpting, and those kind of things. Okay, there's, believe it or not, it's actually really difficult to turn, rotational motion into like a pure translation over a large range. And that's what these mechanisms kind of do. You can see they're just kind of skeleton diagrams, colored lines, but they're linkages. And they're famous enough to get names, right, according to the inventors that designed them. Now, the point that's drawing a line, you can see the dotted line, and the pen is in there. Of course, that point would be rotating, the pen would be rotating, but what it actually draws on the paper would be a straight line. Now, they're only straight within a certain range. You can see the Roberts mechanism is straight as long as this point is between these 2 green points, but once it goes out, it starts curving up. This is a Chevy-Chev linkage. You're going to be using this for your project very likely. So definitely you'll want to remember this and come back and visualize and see how this works. But what this is, if you put a pen in the middle of this, it draws a straight line to some amount, but if you keep going, it'll stray from a straight line. But anyway, this is a really important mechanism to remember. You'll be working with this later. Okay, so this is a Watts linkage. This is a kind of a compact linkage that's used in cars. So it's used in the rear suspension of Ford Rangers and some race cars. The linkage allows the rear axle to travel vertically and not side to side over a certain allowable range of motion. So you can see if it gets too low, it starts looping out here, but for some range, it just goes straight up and down. And it does a pretty good job of guiding over a pretty large range, a straight line, with a very simple design. So you see these in cars and trucks and stuff. Okay, so other interesting mechanisms. Sometimes you want to, sometimes you have power going through a rotating shaft, but you can't keep that shaft straight. You have to bend it. But if you just took a shaft and bent it as it rotates, the other end would just flip around. So how do you have a shaft rotating, but then have a bend and pass that rotation through in a nice, clean way? Well, you can use a universal joint. These are really famous. Famous way to, a serial 2 degree of freedom kind of a joint with a prism joint, or not prism joints, revolute joints that achieve this objective. Okay. So another way you can transmit power from one rotating shaft to another shaft that's not along the same axis, that's maybe bent, or in this case it's 90 degrees. You can see this one's going vertical, this one's going horizontal, is with pulleys or chains that ride along the pulley. And the nice thing about a belt is you can twist it. So this one's 90 degrees, this is coming off here and it's twisted and it goes back on there. And you can transfer the power through belts and those kind of things. So there's very clever ways you can work with belts and pulleys and those kind of things to transfer power from different shafts. Okay, this is a clamp mechanism. This is a mechanism that takes a very small force, but with a very large range at the input. The purple, or sorry, the light, the pink part. And transforms it into a very large force with a smaller range to clamp things in place, like a vice grip to hold it in place. And so basically the point of this is there's all sorts of mechanical advantage mechanisms that turn the small weak force of, say a human arm into a huge powerful force that can do all sorts of neat things, that lift entire vehicles and do neat things. Okay, and then these are cams. Okay, here on the left, we're not going to talk too much about them in this course because they're super easy to design. You don't really need to take a class to know how to design them. Basically, the bottom line is you want to, again, turn the continuous rotation of a motor into some translational output of that's not continuous or nice sinusoidal or something, but a very specific piston kind of translational motion that of course repeats. It has to repeat because the cam itself, this is the cam and this is the follower. The cam of course has to, after 360 degrees of rotation it repeats. And basically the way to design it is, if you know how you want the translational output to be, just take that and wrap that amount around the cylinder or the cam, and that determines the length from the center of its rotational axis to where it's going to push up on this. And if you just wrap it around there, then you can get what you want. Okay, so cams are really easy to design, but very useful, especially if you see that Ryder's automation YouTube video I recommended for you guys in the first video. You'll see they use a lot of cams to do some pretty impressive things. And then gears. Gears, we're going to spend a lot of lectures on gears because they're not so trivial and they're very powerful and they're used all the time in mechanisms, and have obviously, almost any mechanical system uses them, and they've really changed the world. So, even though this is a cool animation, if you stare at it long enough, you'll realize there's something wrong with it, because you can see each wheel starts going faster and faster and faster, and then suddenly this gets slow. You can see this is really fast, but that's slow. So there's some aliasing essentially going on in this GIF, so I apologize for that. But we'll talk plenty about gears. Okay, and the final thing of this lecture is this is a really cool 4-bar linkage called Ackermann's linkage. Okay, and the 4-bar linkage, 1, 2, 3, 4, that's the 4-bar linkage there. And it's usually in the front steering wheels of almost any driving vehicle. And what it does is it prevents the wheels from kind of trying to tear off of their axle and go all in different directions. And, you don't think of it much, but if you think, when you turn a car, you want all 4 wheels to be rotating. You want the car to all parts of the car to be rotating around the same turning axis. And so what an Ackermann's linkage does is it allows this line that's perpendicular to the direction of all 4 wheels. In this case, they share the same line, these 2 back wheels. But these guys, you want those lines that are perpendicular to the axis of the wheel to also hit all at the same axis of rotation. If you had a different linkage, these red lines may intersect this back line at different points, in which point those wheels are going to try and rotate the car around different axes as it turns, and that's either going to tear the wheels off or just cause the wheels to slide and strip and kind of ruin the wheels and lower the efficiency of the car a lot. So what you want is, no matter how tight your turn radius is, you want this point, you want all 4 of these red lines, in this case this is 2 red lines in here, 1 for each wheel, but you want all 4 of these lines to intersect the same turning axis, and it'll pull in more and more for a tighter turning axis. But and when the wheels are straight, this point goes to infinity, and all these lines are parallel. And of course, you'll realize that parallel lines all do intersect. They just intersect at infinity. So this axis of rotation is infinity, and the car will be driving straight. And so this is a really cool linkage that keeps everything rotating around the same axis in a very clever way. Okay, so with that, I hope you enjoyed topic 1, the introduction to mechanisms. We will be covering position analysis is our next topic, and there'll be quite a few videos on that. So stay tuned.